So what we're going to do now is again talk through in real time the SN2 reaction as we did for the SN1 reaction. So this is going to be an example in me drawing it out for you of a generic SN2 reaction. So again, generic, it means it could apply to any SN2 reaction. We're not going to worry about specific substituents. SN2, because it's going to be a substitution nucleophilic bimolecular. So when we see the 2, if it's bimolecular, it means that 2 species are involved in that initial rate determining step. So this mechanism, again, you have it on your slides. We're just going to go through it. So we've got our nucleophile, obviously negatively charged, rich in electrons. We've got our substrate. We'll show it with 3D stereochemistry. So again, just in case this isn't clear to anyone, where we have the dashed bond, that means that group is going away from us. Where we have this wedge bond, it's coming towards us. So all of these materials are tetrahedral, as you will have seen in previous parts of the course before we started this course. So what are we going to do in the SN2 reaction? We are going to have our nucleophile attacking our substrate at the same time as the leaving group departs. So arrows from high electron density to the low electron density, kick out that leaving group all in one step. So our rate determining step, remember RDS, rate determining step is the nucleophile attacking the substrate, losing the leaving group. Because this is attacking at the same time as that is departing, we're going to get partial bonds formed. So if this is our central carbon, we're going to have a dotted line showing we get partial bonding to that nucleophile at the same time as we've got partial loss of the leaving group. So this carbon is this one here. So that of course still has whatever X is, it's generic, so we're not saying what it is. It's also still got Y, it's still got Z. So we've got partial bond formation between the nucleophile and the carbon, whilst the carbon to the leaving group bond is breaking. And this is a transition state, so we tend to put it in brackets, have this sign. So we just note that this is a transition state. We sometimes call it a penta coordinate because pent 5, you've got 1, 2, 3, 4, 5. So some people will be more specific and call it a penta coordinate transition state, but just a transition state is fine. When this bond is completely formed and this one has completely broken, what we'll get is this type of species, so nucleophile with X, Y, Z, plus our leaving group. So this is our final product, and what you will note hopefully is that we've got inversion of stereochemistry. So here, because this has got a set tetrahedral arrangement with the groups sort of this way with the leaving group here, when the nucleophile attacks, now the nucleophile is opposite to where the leaving group had been because that's the less sterically hindered position, so it's easier for this to attack here away from where the leaving group is departing, and so that gives us one isomer. So what we see for this is that we get one isomer of product from one isomer of starting material. So just SM for starting material. And going even further, what we see is that the stereochemistry is inverted. So that's really useful if we're doing our drug design and synthesis and we want to make a single isomer, then if you do an SN2 reaction, we'll be able to make that single isomer. Remember, this is important because different isomers can have different biological and therapeutic properties. So if we want to make a specific isomer, then we could do that using the SN2 reaction. And again, just for completeness, let's just write down the rate equation. Because it's bimolecular and it involves 2 different species, rate will equal a constant times concentration of the nucleophile, concentration of the substrate. So the substrate is this one here, the molecule which is undergoing the reaction. Okay, good. That's another one that we've learnt about.